The wingtip paradox. Look at almost any modern airliner, and you'll notice something at the wingtips. They curve upward, sometimes dramatically, sometimes subtly. Some split into two surfaces, some curve both up and down. These aren't decorative. They're not airline branding. They're solving a physics problem that has haunted aviation since the first wings generated lift. They're called winglets, and they save airlines billions of dollars in fuel every year by fighting an invisible enemy, the wingtip vortex.
To understand winglets, you first need to understand what happens at the tip of any wing generating lift. A wing creates lift because the pressure below it is higher than the pressure above it. This pressure difference is what pushes the aircraft upward. But at the wingtip, where the high-pressure region below meets the low-pressure region above, air doesn't just stay put, it escapes. Air from the high-pressure zone beneath the wing flows around the wingtip to the low-pressure zone above. This creates a rotating mass of air trailing behind each wingtip, spinning like a horizontal tornado. This is the wingtip vortex, and it's a significant problem. Wingtip vortices contain enormous energy. On a large aircraft, each vortex can be several meters in diameter and rotate at speeds exceeding 300 kilometers per hour. They trail behind the aircraft for kilometers, slowly dissipating. From a safety perspective, these vortices are dangerous. A small aircraft flying into the wake of a large jet can be flipped or thrown into an uncontrollable roll. This is why air traffic control enforces separation distances between aircraft, particularly behind heavy jets. The penalty: induced drag. From an efficiency perspective, the problem is different. All that energy spinning in the vortices came from somewhere. It came from the aircraft's engines. The aircraft had to burn fuel to accelerate the air that's now spinning uselessly behind it. This is called induced drag. It's not the drag from the aircraft pushing through the air. It's drag created as a byproduct of generating lift. Induced drag can account for 30 to 40% of total drag during cruise flight. That's an enormous penalty. Reducing it means burning less fuel, flying farther, carrying more payload. Airlines have massive financial incentive to minimize wingtip vortices. The most obvious solution would be to make wings longer. A longer wing has more area to generate lift, so each section of the wing works less hard. The pressure difference at any given point is smaller. Less air escapes around the tip. The vortices are weaker. This is why gliders have extremely long, thin wings. Their aspect ratio, the ratio of wingspan to wing width, is very high. Less induced drag means they can glide further without engine power. But airlines can't just make wings infinitely long. Airports have gate constraints. Taxiways have width limits. Wings must fit within standard airport infrastructure. A wingspan of 80 meters is about the practical maximum for most airports. The winglet solution. So engineers needed another approach. If you can't make the wing longer, can you change what happens at the tip? This is where winglets enter the picture. A winglet is a vertical or angled extension at the wingtip. Instead of ending the wing abruptly, the winglet continues the lifting surface in a different direction. The physics is elegant. The winglet partially blocks the path air would take flowing from high pressure to low pressure. It creates a barrier that reduces the strength of the vortex forming at the tip. But more importantly, the winglet itself generates a small aerodynamic force. This force has a forward component that partially offsets the induced drag. The winglet effectively captures some of the energy that would otherwise be lost to the vortex and converts it into useful thrust. The result is measurable fuel savings. Modern winglets typically reduce fuel consumption by 3 to 5%. On a long-haul flight, that's hundreds of kilograms of fuel saved. Over an aircraft's lifetime, that's millions of dollars. The concept isn't new. Richard Whitcomb at NASA developed the modern winglet design in the 1970s, but adoption was slow initially. Airlines had to weigh the fuel savings against the cost of installing winglets and the slightly increased weight. As fuel prices rose over the decades, the calculation shifted decisively in favor of winglets.
There's an interesting observation about bird wings that's worth mentioning. Many soaring birds have feathers at their wingtips that spread out like fingers. Eagles, vultures, and storks display this clearly. For years, people assumed this was coincidental or served some other purpose. But these spread feathers function similarly to winglets. Each feather acts as a small lifting surface that reduces the strength of the wingtip vortex. The bird achieves lower induced drag and can soar more efficiently. Evolution solved this problem millions of years before human engineers did. We just had to figure out what the birds already knew.
The financial and environmental impact. The economic impact of winglets is substantial. Consider a single long-haul aircraft making one flight per day. A 4% fuel savings might equal 400 kilograms of fuel per flight. Over a year, that's about 146,000 kilograms of fuel saved. At current prices, roughly $150,000 per aircraft per year. A large airline with 200 long-haul aircraft could save $30 million annually from winglets alone. The retrofit cost is typically recovered within a few years. After that, it's pure savings. There's also an environmental dimension. Less fuel burned means fewer carbon emissions. A 4% reduction across the global airline fleet represents millions of tons of CO2 not released into the atmosphere. As aviation faces increasing pressure to reduce its climate impact, efficiency improvements like winglets contribute meaningfully. They're not a complete solution, but they're a proven technology that delivers real reductions.